My name is Eric. I'm going to be walking through our little webinar here on building agents from scratch. But I want to check in, want to make this as interactive as possible. So happy to monitor the chat, answer some Q&A as we go. Really appreciate that we have 45 people here so far. Hopefully we get some more over time. And, all in all, this was a super fun project for me. I don't know if y'all got the chance to see what we built, the parallel GPU coding agents. We put that out a few days ago, and I'll be showing you the thought process of how we built that. I'll be sharing links, general tips and tricks for building one of these yourself. So let's hang out a bit, wait for people to stream in for a couple more minutes, and then we can get started. Where are we calling in from? I see a handful of languages in the chat. I'm here in, I'm normally in San Francisco. The team is primarily based in New York, but we have an SF office and recently joined that. That's been super fun. We got people calling in from Boston, Seattle, NL. Where's NL? I should know that acronym. London, UK. Welcome everyone. I appreciate everyone coming on here. Stockholm, nice. Alrighty, crew. Well, I need to get started here. I have a friend, Felicia, who's helping me behind the scenes manage the stream. So we'll have Q&A bubbled up to me. If you have any questions, please drop them into the chat. My ideal case is every slide or so we have a Q&A that I could jump into, because for me, that's a lot more fun. So just let me know. And let's get rocking. So presentation. This is about building with OpenAI's new agent SDK. I will be teaching you how to build a harness from first principles. So I'll get into the definition of a harness later, but the idea here is, how do you think about approaching building your own custom agent? In our case, we'll be focusing on coding agents, but you could generalize this to deep research or any other background agent that you want to build. You could build your own harness and enable your agents to perform better for your particular use case. So hopefully this is helpful for y'all. Oh, let's see. Am I screen sharing? Yeah, it looks like I am. Cool. We'll be covering the definition of agent versus harness. I feel like people just invent words these days, so we'll be defining those. And then talk about context route, a phenomenon with large context windows, what context windows specifically look like for coding agents, and then we'll get into some context management strategies for longer horizon work. As you can tell, most of this is around context management, and that will be a theme. So one of the big reasons to build harnesses is to manage the context that goes in. Let's see. Let me put my face to the side there so you see the links. Throughout, on every slide, we'll have specific links down at the bottom right, and hopefully my friend Felicia will also share those in the chat as we go. Those will link to whatever is relevant. In this case, we have a blog out about using these concepts to build an agent ourselves. Feel free to follow that for inspiration. Up next, I'm going to be showing you what we're building. This is our own little in-house harness that is optimized for massively parallel GPU research. So we allow an agent to spin up sub-agents, in this case, as many as you need, and put them on GPUs and run something like deep research for, say, OpenAI's parameter growth challenge. And I'll actually, just to tease what you could build with something like this, let me share my screen and I'll show you this live. Let's see, screen share. Let me take down the slides. And you should see my screen now. Cool. So the way we have this set up, I'll go through the code very, very briefly. And during Q&A, if you have any specific questions, I can jump back to the code. But during the presentation, I'll sort of highlight the main things. Effectively, we have a high-level agent that is orchestrating the tasks. It is spawning out a pool of sub-agents to do our on-GPU research. We have sub-agents here that are the coding agents themselves. They run a sandbox on mobile in order to get access to specific GPU types like H100s. And then lastly, we have a skills subsystem that I'll show you how to build. Parameter golf, for those who are not familiar, is a challenge from OpenAI to like try to squeeze as much performance as possible out of a small architecture of a model. So this is the sort of thing that you could really parallelize a bunch of different experiments and let this higher level orchestrator agent delegate tasks to little subagents in order to run experiments, see how they go, scrap experiments that aren't going well, double down on those that are going well. And in the end, we get something that looks pretty much like this, where we have a little Claude Code style terminal into our harness that allows us to do things like spawn 3 subagents to train and mist the data set in each PyTorch, JAX, and TensorFlow. And in submitting this, we submit the job to our top-level orchestrator. It has a series of tools that it runs through, and now it's spawning its subagents, which is a very important strategy that we'll talk about later. And our machines are booting up. Our sandboxes are coming live. You'll see that they should have GPUs attached to them. We'll see. Actually, in this case, it looks like we're doing it on CPU. And that's ultimately a choice up to the model. And yeah, now it's just going through the process of preparing the coding environment and doing the installations. It's going to start the training. I'd let this run through, but for the sake of expediency, let's move on here. But this is what we're building, and this is something that you yourself could build. Feel free to always refer to the demo repo in order to see what this looks like. Awesome. Let me check the Q&A if there's anything in here. Free GPU access. We do have credits for people creating new accounts. Feel free to jump in and try that out. Let's see. Okay, cool. Let's go to our next slides here. Defining an agent. An agent is an LLM in a while loop with tools. I think people are trying to like overload the term of an agent. It's really quite simple. The LLMs decide to run functions that run on your host, on your machine, in order to invoke some tasks. So what you saw there in the demo, a tool is spawn a sandbox or spawn a subagent or get the status of this ongoing process. So those are tools, and an LLM just runs that on the loop until it answers the question that you had. In my case, with my demo, I told it to go train the model, so it's not going to exit that loop until the models are trained. That is the definition of an agent. A harness is everything built around the agent to enable it to do its job. You could argue that tools themselves are part of the harness, but the tools can tie into things like a sandbox, the file system, the skills that I showed you, which is a markdown file. Anything that you sort of scaffold around the core agent loop is the harness. And I'll be going through each one of these points in the rest of the slide. Importantly, context management matters so much. And this is why harnesses really exist, is because models have a finite context window. Once you run out of the context window, they just legitimately can't function, no error out. And a new phenomenon that people are realizing is even before you hit 100% context window utilization, it's just like the models start getting dumb. Like for lack of better words, there's a team from Chroma, you can check out the link at the bottom right there, that did some studies on this, and they termed it context rot, which I think is a good term. Context rot is when your context is so bloated that you start losing accuracy or precision and recall on the corpus of the context itself. So the point of a harness is to control what gets fed into the LLM to make sure that the LLM is only acting on the context that it genuinely needs in this exact moment to make sure that we don't hit this context rot. Coding agents are especially difficult to build because the context is so heavy. Just think about it. Your primary tools that you're interacting with are writing code, reading code, and importantly, reading standard out, standard error from processes, and like that could be massive. If you're running an npm install, there's really no way of knowing how much that's going to bloat the context window. And like you've got to be very careful with these coding agents. They very quickly accumulate so much context that they hit context drought and start becoming very silly. Coding agents get stupid quite quickly. Let me jump into a Q&A here before I move on. Is each agent running on a separate GPU instance right now? Yes. So to answer that question in the demo, and I could go back on the screen share to show the results. Let me figure out how to do this actually. I'm new to. One second. I'm struggling to get rid of this question. There we go. Cool. Y'all can see my screen, I trust. Take this down. Cool. Yeah. To answer your question, every one of these subagents, the way to think about it is the agent itself, the harness itself is running on my computer in front of me. So the actual agent loop, the LLM, the round trips to the LLM are happening from my computer. The agents have a tool. Let's go into exec. The agents have a tool called exec shell in this case, which takes a modal session, which is a handle on a remote GPU, and execs some bash command within the context of that GPU. So it effectively SSHs it over the line. So some similar mechanic. So an important thing here is our harness is separated from the actual GPU compute environment in this case. And for general security reasons, that's recommended. It's good to keep, for example, my OpenAI keys are on my machine, and I don't want that to be in the same exact sandbox security boundary as the arbitrary code that we're executing. So no, each subagent is not on its own GPU, but each subagent has a GPU associated to it one-to-one in order to do its work. On 10 H100s. In this case, it should be pretty obvious that we get GPUs attached to these subagents. But again, the actual coding agent harness for the subagent is still running on my host and is doing back and forth to the GPU environment in order to do its job. Let's see what we get here. Cool. There are our 10 H100s. Note that actually, I was sort of cheeky here. The quantity of GPUs limited. You'll see this in the example code. But the harness makes it so that you can't spin up too many GPUs, so you're not bankrupting yourself. But these agents themselves have H100s available. Give me the NVIDIA SMI from H100 5 subagent. I asked this, and it should boot up this one really quick and run a quick command on it and give us the NVIDIA SMI. If all goes well, now this one is taking longer than expected, so I may bail on the demo, but I hope you understand. All right, cool. We'll go back. Oh, we're moving. It's probably slowed down in the OpenAI end. Hopefully, I don't believe this was any modal issue. And there's our NVIDIA SMI. Sweet. So back to the presentation. On a double, triple check. Hopefully, y'all have seen the screen share that I've been doing. So let me know if that's not the case. And another Q&A. Where's the loop in the agent definition? So I'll promote this really quick. Where's the loop in the agent definition? This is part of the agent SDK. If you wanted to hand roll this, you totally can. For those who are familiar with both the responses APIs or chat completions APIs, there's basically some tag that comes down in the response that says this is effectively a final response or this is a tool call. And you could basically do a while tool call, run the tool, and then feed that back to a model again. But in the OpenAI SDK, they just call it an agent. So you give the agent an input, and then that agent will do as many turns as it needs before yielding an output to you. The UI in the terminal, this is something that we built into the harness itself. There's a, if you look into the example code, it's the Python display.py. Thankfully, with harnesses, you can build whatever supporting infrastructure you want. So that's totally up to you. I personally, I enjoy having a little graphic, status library. But also the interesting thing is if you're building these async agents, you probably want the models to see the same status that you see, because if the status reporting is helpful to you as a human, it's probably helpful context for the model. So that UI is something I built, but it is on top of the data that we want to give to the orchestrator as well. How do you plan to deal with the memory problem in the future? What a fantastic question. That dovetails me into the next slide. Back to coding agents, you can't really predict what's going to come out of the tools. These are the basic tools that you generally have with a coding agent: exec, read file, write file. And exec is especially gnarly because, again, that could be anything. It could give you, thousands of lines, tens of thousands of lines of standard output, and you just can't really control that. There are ways to sort of manually manage the memory, like the context across multiple turns. So a very, I'll say naive, or like the basic approach that you could do is a sliding window. So you just want to retain the last 5 messages in the turn history as you send it to the LLM. But the issue here is you very quickly, you just have destructive forgetfulness. You'll have very important context lost with only a few turns. So you got to be careful with approaches like this. Yes, it works. And in some cases, people apply this approach to just tool call outputs. So, keep all of the chat history, but only keep a sliding window of the last few tool call outputs. That's something you can do. If you have like very image heavy stuff, such as screenshots in like a computer automation case, like you definitely want to sliding window dispose those shots. But generally, like you run into the issue here of you don't want to forget context window. You just want to figure out how to refocus a task to not need that early context, which is part of the context management that we'll be getting into right here. Firstly, subagents, and this is something that you saw in the demo. Subagents are literally a tool that itself is an agent. So in the OpenAI SDK, you have an agent, attach a tool to it, and then in that tool, you call another agent. And then you could add all of this different scaffolding for the agents to report statuses to each other. You will see that in the example repo. But subagents are just agents as tools. The nice thing about this is it sort of gives you this orchestrator agent that is managing everything, but only thinking at the highest level, at a high abstraction. And it makes it so that all of the context flow from the actual task of programming gets encapsulated and eventually disposed with every subagent that we launch. So that keeps the lifetime of like the super bloaty context short. And that also frees up our main level orchestrator agent to think at a higher level async across multiple subagents. So it get more into a coordination type role. In terms of context window, like I said, the benefit of subagents is that without subagents, you're accumulating every bit of context into the agent's context window, and it very, very quickly hits context rock territory. Versus subagents, if you fire them off on a very bursty basis, they absorb, bloated context workloads and then only report the necessary details back to the orchestrator. And that keeps the orchestrator's context window smaller. Therefore, the orchestrator can live longer, do longer horizon tasks. Another thing you could do for planning around context management is something called progressive disclosure. This is, you commonly see this in human systems as well. For example, if you're designing a CLI, in that CLI, you have different commands, and each of those commands has its own help menu. So you don't need to show the help menu of a super deeply nested piece of context unless the user asks for it. This also applies to agents. Progressive disclosure is the idea that instead of jamming all of that context up front, instead let the agent ask to see it. This was a lot of people's qualms with MCP, by the way. The reason there is a lot of backlash against MCP was when you're plugging in MCP into a agent harness, it's just dumping every tool definition of this big long descriptions of every tool that's available to the model into the context window from the very start. And that bloats the context window and it quickly becomes less effective because you're using a third of your context window for just MCP definitions, even if those tools aren't necessary. So a smarter way to do it is implement tool search. Make it so that rather than showing all the tools, you give the model the ability to search across the tools that's available to see. And then you only return, say, 5 different tools. This is something you can build into your harness. And yeah, that's all totally up to you. Let's see. Quick Q&A. Any questions come in? What's the second biggest use case for harnesses versus coding agents? I mean, coding agents, I feel like, is the obvious one because we as engineers are exposed to them. I'm starting to do more personal admin work, like file manipulation, checking my writing. Don't tell the government, but I, reviewed my taxes with my coding agents. Obviously, like I checked it myself, but like people are starting to apply these outside of coding domains. Deep research is probably the other big one that people look into. Adding a search tool, sort of adjacent to the sandbox stuff. Adding a search tool is an incredible thing to give agent harness. So I see it expanding. I feel like deep research is the second biggest use case, but people are discovering just the weirdest things you can do with these. On the topic of progressive disclosure, does this mean creating a tool that lets the model discover more tools? It could mean anything, like anything. Imagine the model has its eyes closed and then you're slowly feeding it context that allows it to be like, oh, let me ask about this. Let me steer in this direction. A file system is a perfect way to think about this. If you have context grouped in a file system, you're sort of implicitly implying there's like this hierarchical grouping of context. So you could imply a rule of only introduce context when like the agent is touching files within this specific directory. This is exactly how Claude.md works in the Claude Code harness, by the way. Whenever you enter a directory, it first pulls in the Claude MD in that directory, but otherwise, that markdown file is not included in the context window. So that is progressive disclosure. Another way to implement it is, as a search tool. In fact, actually, I just realized I have literally the next slide is on this. Skills and memories, or like whatever fragment bullshit, like name the industry gives these things, because it's all context, it's all prompts, but like they're calling it special things. Skills, memories, what it actually is, it's just lazily discovered context. You can do this in a file system, you can put this in an SQL database. People are doing it in vector databases. And then you have different discovery patterns. Like I said, whenever you read adjacent files, just pull in, some blessed like context file, like a Claude MD, when adjacent files are read, or doing an explicit tool to query into these skills, these memories, whatever, or fuzzy search. You can implement this really however you want. Yes. Check that one off. Great. Advanced techniques. These are fun. These are not included in the example repo that I shared with you, but just as like an engineer, I think these are exciting, and I think they show you more how to think about these things and what's available to you as a harness engineer to build them. Programmatic tool calling is one that I think is really exciting. Cloudflare has a SDK around this called Quotas that I think is quite good. And the idea here is rather than the LLMs emitting specific tokens to call explicitly call a function, instead have the LLM emit code, executable code that itself expects your tools to be in global scope. so that if it invokes some tool, it just is able to run it the same way that an explicit tool call would work. For those who know like the internals of the chat, chat completions API or responses API, normally tool calls are sort of a special type of class. But in this case, it just model generates code, you run that code. You definitely need to sandbox this. And I think that's a tie-in that I'd like to explore more on the modal side. We haven't done much of it yet, but you need to sandbox the execution of this because you are executing untrusted code. But the cool thing about this in terms of context management is now all these intermediate tool call outputs are stored in variables. They're not immediately disclosed to the model. The model could choose if it wants to print those variables and see them. But if a piece of like tool call output is only necessary to then feed into like programmatically effectively feed into the next tool calls, then you don't need to have the model see it. So programmatic tool calling allows chaining these things together and only seeing what's necessary. Actually, I'm going to jump up to recursive language models. Very similar concept here. This was a paper that came out recently that I think is really exciting and interesting. Similar to programmatic tool calling is what if you separate the raw context, like just the data dump of everything that the agent is doing, but not actually present that to the agent itself, hold it off to the side, and then have your agent loop have a very, very simple, minimal prompt and just give it tools to effectively search or grep across the accumulating context window that you're holding off to the side. So this, similar to programmatic tool calling, treats the context more like data that you could program against rather than something you just need to jam into the model. And I think this is really exciting. I'm excited to play more with this personally. And then lastly, for those who use Claude Code and other coding agent harnesses, you've probably seen Compaction. This is a pretty simple strategy, similar to sliding window, where you want to reduce the amount of messages or the size of your context window history. And you could use LLMs to literally send the context window to an LLM and say, summarize this, pull out the key points, XYZ. And then that condenses it into a smaller block of history that you could basically continue from that point. That gives you sort of effectively unbounded task length. For issues we'll talk about later, it's not really unbounded, but you could theoretically just keep going infinitely if you keep compressing the context window as you get closer to the limits. And it also removes unnecessary context like real token load that you just want to get out of there. The issues with it, of course, is since you're post-processing it, you're compressing it effectively through the models. It's lossy. If you have very, very specific data, exact lines of code, exact IDs, whatever, in the context window, those may get compressed away. And you'll just, your LLMs simply won't see that anymore, which is a con of this. And then, of course, it's hard to really control or audit how this works. So that is the final advanced technique. Of course, there's many more. And I think a lesson and takeaway from this session that I want y'all to know is you could literally just decide to do whatever you want here. Like there's no rules around building harnesses. It has a word, it has a name, but that doesn't mean it's a specific thing. It's just whatever you need to do to make sure that the context that goes into the model is well suited for what you want that model to do in this instant to allow your tasks to work for whatever length of time that you need it to be effective. So build your harnesses. They're just engineering artifacts. Go add whatever you need. If you have a creative idea, just try it. And I think it's interesting and it works. So that is the presentation. Thank you so much for sitting down with me. Let me run through the Q&A really quick to make sure I'm answering everyone's questions here. Can I talk a little bit about evals? Do you use them to test your agents? There's a huge, sorry, I'm pausing because there's like the correct advice to give and then my honest answer. The correct advice is always eval. Like you need to measure what you're building. For those who don't know what evals are, they're effectively software tests where instead of a pass-fail metric, you have some sliding scale, a score like this was 0% good to 100% good. In some cases, it could be pass-fail, but ultimately you decide how do you determine quality? How do you determine passing in the case of a software system that has an LLM in the loop, therefore it's not deterministic, therefore you can't properly software test it. But evals are your way of doing that. How do you how necessary are they? I think it's very important to have some measurable attribute of what you're building. Though in many cases, if you're building a harness for yourself, this is my own personal take, just optimize for what feels right for you. If you tweak the prompts and it feels like the harness is doing better for you, that's great. If you're building a larger production product, oftentimes, again, this may be sacrilege to say, but oftentimes your evals is usage going up or down. You just track your telemetry and your user analytics. But if you wanted to get really serious and rigorous about it, you could use many platforms. Brain Trust is an eval platform that I really like, and friends of Modal. And again, evals are just effective. Think about them like software tests. They're a code that you write to determine how well your agent is performing by whatever means you need in order to assess that. It could be a model in the loop, calling an LLM to decide, hey, was the output of my agent good? Did it do a good thing? And ideally with a clean context window that LLM judge is able to decide if this actually was good or not. So that's evals. Happy to answer any more questions about that. Here's a good one. Are harnesses necessary for simple LLM API calls? Absolutely not. The OpenAI SDK, the SDK itself is kind of like Lego building blocks to build your own harness. But the SDK has a class called agent. And that agent is quite literally just this for loop with tools or while loop with tools. So if you have basic tools and you just want to do even one term with an LLM, you could give it no tools and just treat the agent like it's an LLM client, similar as you get with the AI SDK or LangChain. But if you had tools, you could do a couple turns and then exit, and it's effectively an ephemeral run, and you don't have to build a harness around it. So don't worry about that. It is not necessary. Looking in the QA. I appreciate it. I enjoyed this talk as well. Hopefully you learned a lot. So in the demo, do we have the capacity to fence the agent from spinning up more than a ceiling number of modal instances? This is an excellent call out because we have exact code that shows that. So let me share my screen and start diving into the code for those interested. By now you should see my screen. And here in the code, it's in the Subagent pool. So part of the harness is this Subagent pool here, which is like a fully software, fully deterministic programmatic pool that limits the orchestrator's access to the pool. So for example, in the orchestrator, let's see, it has lift subagents. So it could check the entries in the pool, or if it tries to spawn a subagent, the pool may reject the creation of that subagent if the pool is at capacity. Or if we go into the pool, you can see up here, we actually have GPU limits set. So these are the fences that you're asking about. These GPU limits make it so that your agent can't spin up a completely out of control spew of GPUs, and then you end up paying for that. Though in the harness, if we wanted, I don't have limits imposed for non-GPU tasks. So if we did CPU stuff, I could say spin up 100 parallel CPU sandboxes. I will say in advance, 100 tool calls is probably going to crash this demo, but we'll just run this for fun. And this is totally fine because we haven't imposed a limit on CPUs, but we have imposed a limit on GPUs. So again, going back to harnesses or just software you write, you could just write a limit into the pool, and that's totally fine. There's nothing inherent about the agents SDK or harnesses as a strict definition that says you can't do that. So it is totally up to you. I want to see how this does. I haven't tried it up to 100. had like 20 running before, and that was fine. But let's see what happens here. It actually may crash my little graphics library here since the library renders on the screen. We may have to check back in on this one later. OpenAI is slow today. I'm not complaining. I understand this is a live demo, not making excuses, but this actually does feel slow. Oh, there we go. Cool. So, and the dot 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 down here implies 100 sandboxes. There we go. So they're idle. They're going to shut down automatically on Modal. I'll just say, I'll do some housekeeping. Always thank your models. I think it's good karma. And we'll just do some cleanup after ourselves. Back to the press. Cool. So hopefully that answers the question about fencing around GPUs. Here's a good one. So how do you think about staging? How do you force a certain progression of first we do this step, then we do this step, then we do this step? There's an excellent, for those who follow Swix and the AI Engineer podcast line, there's an excellent talks from a guy named, what's his name? Dex, I believe. Not Dex, no. I'll have to pull up the link, but I'm sorry, I'm not being helpful right now. The human layer, his name may be Dex. Either way, he sort of made famous this idea of, I think it's observe, plan, execute, like a strict loop that you want to go through with your coding agents to make sure that they first gather all the context they need, they create a plan, and then you take that plan, compress just down to that plan, and then you execute off of that. So the execution doesn't have to worry about all of the extra context load of the exploration and the observation phase. And the the challenge of these multiple steps is you now need to think about agents in multiple modes. And one thing you could do there, this is, I mean, there's so many things you could do here, right? One approach is the Agents SDK gives you something called hooks. These hooks allow you, basically it's on tool call or on LLM call or on LLM call exit. They're hooks that you send into the agent that are basically like function callbacks. So you could say, like, you could effectively turn it into a state machine of when the LLM is invoked, transition your harness into a new state, a new operating state that is the plan state, and maybe that plan state has different opinions about what what context, what history you send into the agent for this particular run. So you can do it through hooks. You can also do it through tools. Just ask the model, hey, turn on plan mode and start doing this, and then the model can invoke a tool that flips a internal representation on its own class definition that says we're in plan mode. And then the next step, the next turn, you could do it within the context of plan mode. So how do you think about this? The determinism around it's like relatively hard. There are some more explicit libraries. For example, LangGraph allows you to build deterministic steps. And Agents SDK, I haven't explored it too much, but they have this primitive called handoffs. The whole idea there, rather than an orchestrator of subagents, you literally just like dispose the orchestrator and then pass it off in a handoff to the next agent, a bit more like a compression style thing or compaction. And if you write your code in a way where you create an explicit three-step handoff of first you have explore, then you have plan, then you have execute. Cool. Now you give your execute sub-agent or your execute agent sandbox. You give the other ones. I guess the explorer probably need a sandbox as well. But that allows you to sort of encapsulate different prompting logic and different context windows into each step of the way. And using handoffs would make it a bit more deterministic. So like there's a bunch of different tools there. I couldn't call out to more specific things. But, and then, I mean, sorry, lastly, there's like fully deterministic systems like N8N. And again, light math allows you to do this deterministically. But in my experience, the models are pretty good at following instructions and knowing where to go. For example, in the harness that we built, there is a tool that allows it to set itself to high planning mode, like extra high, like the reasoning settings for the LLM, and pretty reliably like flips that on for harder tasks. So if determinism is required, go find a tool for it, but I generally think it's not as necessary anymore. Which harness did I use? This is hand built. We're building a harness from scratch. And the goal here is to show you like if you're building a cloud code or an open code, like if you're on that team or if you wanted to build your own, how would you go about it? How do you think about this? So thanks for the question there. Could we share the presentation, please? Hopefully, actually, I'm curious. Felicia may chime into the chat around this. Um, the I believe these slides should be available in the link. I am new to this. This is my first live stream, first webinar, so thanks for bearing with me. But I believe you should have access to those. If not, I'm sure we'll send some follow-up to webinar attendees with all the content that I covered here. Oh yes, in Rashmi's response in the chat, thank you so much for sharing Dex's talk from the YouTube. Definitely check that out. I think a lot of what we talked about here is very inspired by a lot of the content he's put out. I think he's a great speaker. So go check out the chat. There's a link to a YouTube. I think that's a good follow-up here. Steve from OpenAI, thank you so much for jumping in. Appreciate that. Let's go to computer use. So computer use examples, some fun lore actually. I recently joined Modal. I was previously running a startup that got acquired into Modal. And we started as a computer use company. So I have a lot of opinions about this. Probably too many. I don't want to like poison the vibes of this webinar, honestly. But computer use is totally possible. We have an example. I believe we have an example on our demo site of booting up a headless UI for a Linux machine. Browser stuff is also interesting too. We see some of that. I do think computer use has like very special, I'm not talking you out of it, but computer use does have like some special considerations. For example, oftentimes bot detection uses the IP of the sandbox in order to detect that it's a bot and it may block you. So generally, when you start getting into super hardcore computer use cases, you may end up on a different platform. But like ultimately, if you're building a harness for computer use, the most basic thing you could do is a tool to screenshot, a tool to click at some coordinate, and a tool to type some text. With that, you have the basic loop you need of screenshot act, screenshot act. And you could do that in browsers, you could do that on desktop environments, and all of that theoretically could be stood up within a mobile sandbox environment. And then from there, if you wanted to dig deeper, you could get into, actually, this is a good tie into the programmatic code, programmatic tool calling thing that I talked about earlier. That this was the reason I got excited about it. Is computer use in these other automation cases actually do very well chaining together multiple tool calls, because it's ultimately just an automation, it's a flow, but the model needs to discover it. So if you tie things like this, where you're generating JavaScript or Playwright code to just go in and execute against a browser, like that's a pretty good approach for computer use. Let's see. Which SDK do you find the best so far? I love all my children is my response there. I do think the OpenAI SDK is a really easy sort of Lego style SDK to build harnesses around. When I was building my harness, I genuinely felt like I was writing my own code. I was building my own system. And when I needed LLMs or when I needed session memory, for example, it's just super easy to treat those as variables in internal state in my system and then pipe them together as needed in order to, execute some calls. So OpenAI, I think, is a really, really good SDK. I've heard great things as well about Pydantic's SDK. I'll shout them out. Great work on their SDK. And I've handled my fair share of agent moves, which honestly is kind of a pain in the butt. It's just a lot of enum handling of the different response types that come back from the APIs. But thankfully, a lot of LLM providers are standardizing on the same APIs anyway. And that allows you to, once you build your own handle, you could just go out and use that. So you sort of build up a muscle for parsing tool call requests and executing them. Though I will say my go-to right now is OpenAI. I think it's a great library. Mhm. Do you have a manual or demo code in GitHub? Yes, we do. That is in the slides here. I hope you can see the slides after this, but if you were to, right down here, Modal Labs / OpenAI agents Python example, you can definitely pull that up, and that will show you the exact thing that I demoed to you that you could use to go off of. We also have a companion blog here, modal.com/blog, building with Modal and the OpenAI agent SDK. I wrote it, so I'm biased, but I think it's a great blog. It talks through a bit about what we talked about here, but it also covers the specific API service area of the OpenAI SDK. So I'd recommend checking that out. Here's a good question. Do you get a sense that engineers will be spending our time more building the harness versus evaluating the harness? I don't know. Some teams spend a whole lot of time writing software tests and some teams don't. And they let themselves see the results just by smoke testing, and like manually going through and QAing the app themselves, or just seeing what user metrics say. I'm not saying that's the right approach. I think the correct approach is evaluating. But I think this is really a personal preference thing. I don't think there's a correct answer here necessarily. I personally, I find a whole lot of joy in writing the harnesses, and I feel like I have a good enough sense for what feels right and what doesn't, that I'm spending less time evaluating, frankly. But once you start adding more people to the team, just like the software tests, now the context isn't the human context isn't as, tight with yourself. So in order to prevent regressions, it is nice to have evals in, just to have a sort of canary in the coal mine thing of knowing if some change goes into your code base. Put your evals on CI to make sure that you at least see what's happening. But it's ultimately a stylistic thing. I think, let's see, I haven't fully read this question, but it seems interesting. How do you manage harness memory tool interaction? Without proper interaction between harness and memory, memory alone is powerless. Memory operations, including retrieval prioritization, compaction, should be native and baked into the harness. So if I understand what you're asking, there's specific memory constructs built into the OpenAI SDK. For example, there's something called session, and that's basically an SQL or some other, persistent storage backed way of tracking a thread of turns. A turn is a single back and forth to an agent or to an LLM. And those turns, appended to each other over time creates a session. And when you reuse that session with an agent invocation, you're effectively giving the agent the same context window as before. In all of our examples, we aren't modifying the session ourselves. For example, if I jumped to sliding window, get rid of that question here. If I jump to the sliding window context management strategy, you would sort of need to break free of OpenAI's sessions construct, or most likely they have SDK, like APIs built into this already to trim down a session to a specific length, and like modify the session in place. So don't quote me, but you may need to break free and start managing, the context window, like the accumulation of messages in the context window for the agent. You may have to do that yourself. This is also the case with compaction, for example, where you're rewriting history effectively in the eyes of the model. So you may have to dig in and manage that at a harness level versus depending on OpenAI's SDK. Though again, in our case, like with subagents, the subagent strategy allows you to view sessions and context windows as much more short-lived. Therefore, you don't need to do as much maintenance and pruning of specific details within the context window. You can just basically start a new session with a new subagent. And that coupled with things like progressive disclosure, generally, if you drop and like skills, memories, things like this, if you drop an agent with no context into an environment that it has access or it has signs that it can start poking around and see things like skills, see things like memory, it has tools that it's aware that could fetch, maybe a list of other tools it could call. As long as you like leave these breadcrumbs for a fresh agent session, generally they can reconstruct their own state. So it's on you to like, are you designing breadcrumbs for the model, or are you designing a way to compress, edit, revise its own memory history in a more like heuristic based manner? I personally prefer, I think my experience with agents is they generally, when you mess with their history, um, I don't know, it's harder to empathize with. I genuinely think, not to anthropomorphize models too much, but like thinking about them through the frame of what would I be like if I was presented this information is helpful. And the idea of a linearly accumulating context window allows us as humans to better model sort of what, like empathize for what that model may be seeing and understanding where it may have fault like drawbacks. Um, but the editing history thing, it's a bit harder to like ourselves wrap our brains around that versus the idea of, oh, we just clean slate, start it with no context and building context up over time. So I generally prefer not diving too much into modifying session memory. I prefer handoffs or subagents in this case, but that's ultimately up to you. Mhm. Here's a great question. How important is it to align the model you use with the harness? So to rephrase this, some models, and like this is, you could eval this, you could certainly like quantify it, but just subjectively, some models do better with a harness than other models. And it's just like the way those models are accustomed to interacting with, the specific tools you may presented, how in just distribution were those tools or similar functionality when this model was trained. So there's definitely sort of a co-design thing going on, making sure that the harness you're building fits the model you're working with. Um, with coding agents specifically, and like, in the OpenAI SDK, for example, the sandbox tool set is actually pre-baked into the SDK. It's predefined. And I suspect that's relatively intentional of the labs want to sort of define, here's the general interface we're going to train against, pre-training, post-training. RL, here's what we're going to train against. And then as long as you stick with those standard tools, you could generally use the models interchangeably because it's very like, you have no idea the degree to which these labs are training on just exec as a tool call. Like that itself is, every lab is focusing on that because every lab recognizes it's powerful. So if you have standard tools, I wouldn't worry too much. If your tools are super, super niche, then you may need to eval the different models you're running on the back end to make sure that you're not, running on some suboptimal model that likely hasn't seen something like this in its training set. So um, I generally wouldn't worry about it, but it's a great question to ask. Awesome. I'm going through the Q&A and I feel like I've answered most of it. If there's any other questions that come up, let me know. I'm happy to hang out in the chat here. Otherwise, I believe we may wrap it early. Thank you so much for coming. Thank you so much for being a part of this. Again, this is my first webinar. I had fun. I hope you had fun. And I hope you build some good agents. So have a good one. I'm down to hang out in the chat until the end, though. So just let me know if you have any more questions. Awesome. Thank you, everyone. I think we'll wrap it here. It seems like there's nothing else in the chat. So y'all have a good one. Thanks for being with me.